Alright, so to start off this section, I'm just going to do a short review of polar coordinates. So this is probably something most of you have seen either in trigonometry or pre-calculus or something of that nature. And really what polar coordinates are is just another coordinate system that's used to describe a plane. So the one we're used to working with is the Cartesian system, where you specify the horizontal and vertical components individually, so x and y, and then that describes a point. And the Cartesian system does it uniquely, so for any specific xy pair, there's only one corresponding point. Now polar is similar, although it also takes two different values. It has r, well actually, theta and r. So, and what those are, so this is what a polar graph looks like. So this is called the polar axis, and this is kind of our reference for making angles, and angles in polar so are measured counterclockwise. So if we were to say theta, it would be measured in the counterclockwise direction. So to specify a position in polar, all you really have to do is specify the angle and the radius, and this would specify this point. Now the thing that's a little bit different in polar is that each of these representations, each point has a lot of different representations. For instance, if you were to take this representation, so we have theta and r, let's just call that 1, and then you were to use theta plus pi minus r. Okay? So then instead of being theta, this was our original theta, we're adding pi, so we're going to be all the way out here. But instead, when r is positive, we're extending outwards, but when we flip the sign of r, it points in the opposite direction of where it would normally if it were positive. So instead of going in this direction, it actually returns to the same original point. So basically, theta plus r comma negative r is the same exact thing, because we put it on the same line and then flip it back by using the negative of r. So that just goes to show, and you can do this for multiple iterations of pi. It doesn't necessarily have to, you could multiply this by 2 pi or something like that. You can do it many times, and you can also flip this a lot of times. And there's just a lot of different ways of representing a point, infinitely many ways of representing a point. Now, the natural question is, okay, they both represent a plane. Why would you use polar? Well, polar is quite useful in problems where there's a symmetry around the pole, which is this. So a radial symmetry. If something like a circle, for instance, it's usually easy. Well, it is easier to represent a circle in polar rather than Cartesian, and in some instances it's also easier to represent maybe a line if it's going through the pole, and Cartesian is usually easier for like vertical and horizontal lines and things like that. So there's infinitely many coordinate systems you can use to represent any given system. It's just you want to pick the one that symmetry makes it the easiest. Now the next question is, okay, well, if they're equivalent ways of expressing things, how do you go between them? And let's just start off by drawing another graph here. So if we have a radius and some angle, the question is, okay, we've specified our radius and angle, how do we get to Cartesian? Well, if you remember from trigonometry, what we can do is drop down this perpendicular here, and then we have a right triangle. And with a right triangle, we have a lot of different proportions, trigonometric proportions we can work with. One of the first ones, so this would be our y and this would be our x, is we know a couple things. We know that sine theta is equal to opposite over hypotenuse, which is equivalent to saying, well, y over r is not necessarily useful because they're different systems, and we want one system on one side and the other on the other side, so we can convert. So if we multiply over by r sine theta equals y is a much better way of expressing it, as far as if we have an r and we have a theta, we can find a y. And then equivalently, we have cosine theta is equal to x over r, and then, well, r cosine theta is equal to x. So, and this comes up a lot in physics if you're talking about the x and y components of some sort of vector, maybe a force, maybe a velocity, something like that. You break it up in this way. Okay, so those are two of the necessary things. And then the third one is that we know tangent of theta is equal to opposite over adjacent. And this is useful for finding the angle in between. If we're in Cartesian, we can find the angle by taking the arctan of both sides in between the vector. Now, the only thing about this specifically is we don't necessarily know what quadrant y and x are in, just because y and x, well, if we think about it, let's just say we have some x naught comma y naught, and in the opposite direction, in the same horizontal and downward, just opposite sign, we have negative x naught, negative y naught, right? Then if you take the ratio between the y coordinate and the x coordinate, negative y naught over negative x naught is the same as y naught over x naught. So it's just important to figure out which quadrant you're in when you're describing something like this. So that about summarizes the four main, oh, I only did three, there's one more. The last one is pretty simple. It's just the magnitude of this position vector, so to speak. We can say that using the Pythagorean, x squared plus y squared is equal to r squared. And that summarizes the four main ones being, so we've got this guy, this guy, this guy, and this guy. And with those four, we can completely convert between Cartesian and polar, given different positions. And now the next idea is that, well, now that we've done that, we also want to be able to write functions, because these are just positions in polar. Now, it's similar to the Cartesian system where you have y as a function of x. In polar, you have radius as a function of theta. So what that's saying is, depending on what theta you're at, you have a different radius, and this can create all kinds of different shapes that are very hard to depict in Cartesian. Maybe some sort of swirling shape or something like that, where the radius is getting bigger as we go around with theta, something like that. And then once we have these functions, radius is a function of theta, we can start differentiating, and we can start integrating and solve the standard calculus problems of derivatives and integrals, and to find slopes and areas. Alright, so let's just work out one example, or a couple examples, I guess, of converting between them. So let's just say you had the system r squared equals, well, not the system, the function r squared is equal to 5 in polar. Well, to get that into Cartesian, you would just look at your four different expressions, equations, and you would see that this one clearly, right, if you just replace x squared by r squared by x squared plus y squared. And then you would see that, okay, well, r squared equals a constant is a circle in polar. Well, yeah. So that's that. And it's a circle at the origin, so centered at the origin, that's important. 0, 0, center, and a radius of, well, root 5, because this is radius squared. Okay, so that is one type of conversion that pops up a lot. Another thing, if you were going from Cartesian to polar and you had something like y equals x, well, it's a line, we know that, and it goes through the origin, and because it goes through the origin or the pole in polar, it's very convenient to also write it in polar. So to specify this, going from the polar axis, we really just have to write a value of theta, because the radius, the theta is not changing. Theta is constant, and no matter the radius, right, the radius is just extending outwards infinitely. So from there, we could just specify what that theta is, and we've completely described this line. because all it really is a slope. There's no y-intercept, so all we need is theta. So in this case, y equals x. Well, we could divide over by x and get 1, and then we know that that is equal to tangent theta. And then we could say, okay, well, inverse tangent, let's see, inverse tangent of 1 equals theta. And when does that happen? That's theta is equal to pi over 4, because sine is root 2 over 2 and cosine is root 2 over 2. So this would be the description and polar of that line. So hopefully that little summary of why polar is useful and the different conversions helps out.